Sure. Our next speaker is Marko Bevc, and he's talking about seamless scaling of Kubernetes nodes. Over to you, Marko.
Cool. Thanks, Danny. Thanks, Adrian. Really impressed with the pronunciation then. Thank you. All right. Let me try to share my stuff here. Cool. Hopefully everybody can see that. If you can't, please give me a shout. But I will just assume that that's currently visible and in a good shape. So welcome to the last talk of the conference today. I have to say I really enjoyed it so far. I really like the variety of different talks that we have. So all the way from deep down in technology, as Josh did it now, all the way up to a high level and kind of environmental talks that I think are quite important as well. So what I'm going to talk today about is we're going to have a look at the seamlessly scaling of Kubernetes nodes. So it seems like a really mouthful title, but what we're going to look into in a nutshell is, are there any alternatives to kind of the auto scaling that we're currently doing in our Kubernetes nodes? So first of all, I would like to start with a quote, "Be water, my friend." And this was actually a quote from Bruce Lee, who was a martial artist, actor, philosopher, and a filmmaker. It was actually captured in the Canadian show in the 70s. It was called the Pierre Branson Show. So Bruce Lee gave an interview there, and he talked about the mentality and how he approaches things in life. And what he was trying to say with that is that in the kind of highly hybrid and like fastly changing environment, you need to keep your mind open to new things, and you shouldn't kind of cling on to like conventional norms. And that's why he kind of talks about being shapeless, formless, like water. So for example, like if stream goes down the hill, it always kind of tries to adapt to different kind of obstacles down the way and tries to go around it. So who am I? I'm Marko, as already kind of said before. I work as a senior consultant at the Scale Factory. We are remote-first DevOps consultancy based in London. And we're also AWS Advanced Consulting Partner and Kubernetes Service Provider. A little bit of a disclaimer / kind of a heads up here. Even though we're going to talk about the provider independent solutions today, all the examples and the demo will be shown on the AWS infrastructure. So hopefully you can apply that to different kind of vendors as well. My background is mostly ops, so I have an extensive kind of knowledge with Linux and virtualization from my past kind of engagements. I'm also an open source contributor and a supporter, and a big fan of automation and simplifying things. If you can still remember pre-pandemic, I also really enjoyed traveling, cycling, and hiking, which was a little bit limited lately, but hopefully we're going to get there soon. So what I'm going to cover today is we're going to kind of kick it off with, some scaling foundations. How does the Kubernetes resource scaling look like? We're going to have a look at the kind of automation options there, and going to try to see what the current kind of limitations or drawbacks are using what we're currently using for auto scaling. And kind of going from there, we're going to look at one of the projects that is trying to address this. It's called Carpenter, and it's trying to kind of change the idea a little bit around, and it's trying to do groupless auto scaling. So we're going to have a look at the architecture of the project, how they're approaching those kind of problems, how they're doing scheduling, how it's done bin packing, and also the whole capacity lifecycle. From there, I'm going to go with a demo. Hopefully the demo gods are really good. I'm satisfied with the sacrifice this morning, but everything should be on track. And I'm going to wrap it up with some takeaways and project status at the end. Okay, so if we quickly go through the scaling kind of fundamentals. So if you look at scaling, we can either have horizontal scaling, which usually means adding more instances, and this is usually referred to as scaling scaling out. And then you could have vertical scaling, which is usually referred to as scaling up. And in this case, you would add more power to your existing instances. So in terms of Kubernetes resources, we can scale either pods or nodes. And let's first have a look, where do the pods come from actually? So we can actually end up with pods by manually spinning them up using CLI, or we can actually provision workload resources such as deployment, replica sets, daemon sets, jobs, and those would take care of provisioning your pods afterwards. Looking from the kind of auto-scaling perspective, what we can do here is, in order to react to different kind of environment requirements, such as influx of requests, we can use tooling such as horizontal pod autoscaler or vertical pod autoscaler. Just bear in mind they're mutually exclusive, so either use one of those. There is a different autoscaler available in GCP, which is called multidimensional pod autoscaler, and it's trying to kind of combine both of those words together in order to kind of be able to scale up pods horizontally and also scale them vertically as well as needed. There are also some other tools in this landscape available as well, such as Kata, which is an event-driven autoscaling, or Knative, which is a service platform, which kind of also gives us the autoscaling functionality. Okay, those are pods. Let's have a look at nodes now. So obviously, you can also manually provision nodes as well. But from the automation perspective, probably the fact of standard in the industry today is probably Cluster Autoscaler, which is probably most widely used. There's also a Zalando fork, which is trying to kind of address some of the limitations or kind of caveats around using Cluster Autoscaler. And there are some less maintainable projects such as Libro and Escalator. So let's have a look into the Cluster Autoscaler right now. So Cluster Autoscaler is kind of an industry-adopted, open source, and vendor-neutral autoscaling solution. What it does is automatically adjust your cluster size based on the load that you're currently running, and it tries to be cost-efficient. So it tries to keep your infrastructure cost-efficient and as lean as possible. It is battle-tested, so you can use it up to a couple of thousand nodes with 30 pods per node. And it's using existing cloud building blocks. So for example, on AWS, it would use autoscaling groups in the background. But it also comes with some challenges, right? So because it's kind of relying on the autoscaling groups in the background and the kind of node groups, which are kind of an abstract term in Kubernetes world, you're obviously limited to specific kind of concept limitations here. So for example, if you want to span across multiple AZs or use different instance types, you would usually need to provision multiple node groups to kind of achieve that as well. So obviously it kind of works on the premise that you're using the same templates in the background, and those would be applied to the whole node group, not specific nodes itself. It's quite complex to use as well. So it has, I think, like over 70 arguments that you can use when you spin it up. It's quite tightly bound to the scheduler. So part of its code base actually uses the specific version of the kube scheduler. And that actually makes it a little bit harder to port, or at least you have to use the compatible version with the Kubernetes version that you're currently using. And it's a global controller as well. So, at this point, there were some smart folks at AWS, and they actually thought, okay, we can probably look at this from a different perspective, and we can probably kind of solve some of these challenges by, changing a few concepts in how we kind of provision resources in Kubernetes. So what is Carpenter? It's a node lifecycle solution. It's currently incubating in AWSlabs, also open source, and vendor neutral, even though currently it's only supporting the AWS provider for obvious reasons, but it's vendor neutral, and there is a kind of wide adoption plan for later on in the project. And what it's trying to do is, if you look at the diagram here, you couldn't really see the difference from the autoscaler, but the logic is a bit different. So instead of using the kind of the cloud building blocks, it's directly provisioning capacity. And it's doing that by using pod resource requests. And based on those, it's calculating the instance types, because you can actually query for all the instance types that are available to you. And then they try to kind of simulate how those pods would kind of fall into the instance types, and then request the instances that would kind of satisfy the resource requests. They're also generating node properties on the fly based on the pod scheduling constraints. So everything is kind of done on the fly as the request comes in. So it's much more flexible in this regard. So it literally removes the whole node group concept, and thus it's usually kind of referred to as groupless node autoscaling. By doing that, it really lowers down the cloud provider API utilization. So there are far less API calls that need to be executed, and also reduces configuration complexity as well, because it's kind of using the common cloud native approaches to kind of configure controllers using the CRDs. So if I quickly look at the provisioner CRD that you need to kind of use, you can use one or many of them. There is no limitation to it. And there is a question of what use cases would you like to kind of address with it. But let's have a look at the most kind of simple CRD that you can use, which is kind provisioner from Carpenter.sh. And in the specification, you can see it's not a lot of parameters that you would need to provide. So you need to specify a few kind of cluster parameters, so it knows which cluster it connects to. I think there is a thing on the roadmap to kind of auto-calculate that in the future as well. And then a couple of others around setting TTLs for nodes and specifying taints for those. And also you can specify additional constraints, which we're going to look into detail in the demo later on. So let's kind of dive quickly into how the launching capacity works. So they're launching capacity by directly executing the API and using the EC to create fleet API calls, and that kind of returns the whole capacity needed. Under the hood, they're using a couple of controllers to kind of launch the capacity and manage that. So there is an allocator controller, which is a fast, latency sensitive one, and the reallocator, which is a slow and kind of cost sensitive. And that brings the provisioning latency down from average, which is on average 2 minutes across the providers, down to around 60 seconds, which most of the time is currently still used on provisioning the node itself rather than scheduling. So the scheduling is usually kind of provisioning the resource, and this is implicitly doing the scheduling as well. So whether you like it or not, when you provision a node, you're kind of already hinting the scheduler where this node is going to kind of get spun up. And they're even kind of helping the scheduler additionally by binding it to a specific node, because this is the information already available during the provisioning phase as well. And in order to kind of decide which pods bin to specific nodes, they use online bin packing. It's a kind of a well-known term in computer science, and it's an incomplete problem where you try to fit your capacity, kind of request for capacity to a kind of limited capacity you have. And they're using the first fit scheduling descending algorithm to achieve that. So it's loosely coupled with scheduler, even though it's kind of tightly working with the scheduler. It's not relying on the scheduler explicitly. And if you remember the code before, it definitely sounds like they're trying, or at least the Carpenter trying to be more like water. So it kind of adapts to different kind of requests from the environment and tries to be flexible and kind of efficient in provisioning that as well. It also supports all well-known labels to kind of limit where the pods will be assigned to or what kind of nodes you want to provision. So what's left in the lifecycle, capacity lifecycle then? So Carpenter is also kind of taking care of the termination of the resources. So as soon as the node is emptied, the TTL is assigned to it, and as soon as TTL kind of expires, the node is being terminated. They're also kind of making sure that underutilized deleted nodes are cordoned and correctly trained. So there is a finalizer as well. So if you manually delete a node, it will train the node before actually removing it. It's reacting to spots and rebalance kind of termination events, instant unhealthy events. And there is an interesting kind of a use case here as well. You can set an expiration TTL on the node itself, which is a really good use case for compliance. So what you can actually do is set an expiration date or an expiration TTL on a node, and that would ensure that the node would be terminated after this expires. And as you can imagine, this could actually keep your cluster up to date automatically. There is the fragmentation they want to implement as well. It's still in the design phase, unfortunately, but the idea is that you shouldn't be stuck with initial provisioning. So as your nodes become less optimally utilized, we should have a controller there kind of kicking in and taking care of that and just moving the workloads across as requested. Obviously, that comes with additional complexities and different challenges, which are trying to be addressed in the project as it kind of goes along. Okay, before we dive into demo, I would just like to kind of set the scene very quickly. So what we're going to do here is, as I mentioned before, we're going to run the AWS EKS, which is a managed Kubernetes cluster in AWS. We're going to use Fargate profiles. And the reason why I think this is a really good use case for Fargate profiles is because obviously there is a chicken and egg problem, right? So you say, okay, I want to deploy an auto-scaling solution, but obviously you need to kind of provision it somewhere. So either you statically provision a node and run it there, or you can just use AWS Fargate, which is a serverless solution, kind of nicely embedded into the EKS, where you can just delegate everything to AWS, and they will kind of provision the underlying resources for you. And I think provisioning Carpenter and the kube system namespace there is a really good use case here. So as soon as we add workloads, the Carpenter will take care of and provision our non-Fargate workloads and schedule the workload there. Cool. Let's quickly switch to console and let's see what we got here. Hopefully that's big enough. Adrian, please shout if this is too small. I can make it bigger. I will take that as a yes. Cool. Let's have a quick look. So what we are currently running in here. What I'm currently running in here is, like I mentioned before, it's a kind of a vanilla cluster. It doesn't have anything in it. We just run core DNS. There are proxy and CNI bits waiting to be spun up as soon as we have additional capacity available, but they are not necessarily needed for the cluster to run. And we obviously run Carpenter controller and a webhook.
If you can make it any bigger, Marko, I think that would be good. When it goes through to YouTube, it's a little bit
small.
Yeah,
absolutely. Better?
Even bigger, I think. Yeah, good. Thank you.
Perfect. Let me make the other ones the same as well. So we're going to end up on the same thing. Okay. So this was actually deployed using an upstream Helm chart, which makes it quite easy to deploy. And we're using the latest version to achieve that. So what we're going to do first is let's quickly have a look. We need to deploy a provisioner. Like I said before, we're going to use a provisioner. We're going to connect it to the cluster we're running it in. We're going to say TTL seconds after empty to 30. So it's going to terminate nodes after 30 seconds after they're being emptied. And we're going to limit it to 2 zones, only 1A, EU West 1A and EU West 1C. So we shouldn't be getting any nodes in EU West 1B. And we're going to limit the instances to a specific set of instance types we want to use. So obviously we don't want to use super expensive ones, and we want to avoid the small ones as well. Okay, let's quickly provision deploy the provisioner. So the provisioner is deployed now. And the next thing we're going to do, we're going to kind of run a really simple deployment. So what it's going to do is just going to use a pause container, so nothing really fancy. And the reason why we're doing that is we're going to request a 1 CPU. And the reason why we're doing this is by using CPU requests, we're going to force the resource exhaustion, and thus the Carpenter should kick in where kube scheduler won't be able to kind of schedule the pods anymore. Okay, so let's create a deployment. So we're gonna quickly check the pod. So we're not running anything yet because deployment is currently scaled to 0. And what we want to do here as well. So what I'm gonna open here as well is, sorry, I'm gonna open logs from the Carpenter controller. And the next thing we're going to do, we're going to watch for the number of nodes that we're currently running. So currently we're only running 4 Fargate nodes to kind of run the Carpenter and the core DNS and nothing else. And what we're going to do here first is we're going to scale the deployment up to 1, right? So this is very simple, scaling up to 1. And as you can see here is we don't have any capacity available yet. Because the default namespace cannot be scheduled on Fargate. Thus, the scheduler marks this pod as being pending, so it's currently unscheduled. As we can see in the logs from Carpenter, you can see that Carpenter actually detected that. It kind of seen that there is one unscheduled pod, and it actually calculated the instance that we can actually use to kind of schedule this pod on. So it's computed it. There was a set of instances that we can use, and it decided that the most appropriate one is actually c5.xlarge. And because we're using constraint, it's going to go to EUS 1A. And if we look at the nodes, you're going to notice that there is already a new node being spun up. Currently, it's in the unknown status because the node is still booting. Oh yeah, here we go. It's not ready currently, but as you can see, in about like 60 seconds-ish, you actually get a new node provisioned with an instance type that kind of could fit the workload. And it's limited to a specific zone that we specified in the provisioner as well. So if we quickly have a look at our pods, you can actually see the container has already been created. So the image is being pulled down, and the container should be up and running already. Okay, so let's move forward. So let's say we want to scale it even further, right? So let's scale it up to 3 replicas now. So if we look at the containers now, you're going to notice, oh wow, all 3 of them are already running. And the reason for that is because the instance that has been spun up had enough capacity to kind of schedule those. And if you look at the log, there is nothing in log. So Carpenter didn't actually kind of kicked in because the controller loop didn't detect any of the unscheduled pods. Okay, so let's scale it even further, right? So let's scale it up to 7. This should kind of kick it in properly. So as you can see, we ran out of resources, CPU resources on the node, and we ended up with 4 unscheduled pods. And Carpenter detected again, we have unscheduled pods. It tried to kind of do the bin packing and calculate from the instances that we are limiting it to which one could actually be used to fit 4 additional pods. And it decided the C5 to X large should be good enough to kind of provision it. And this time it actually went with EUS 1C, which is another zone that we kind of limited to. So there was another loop going through. As you can see, the second loop actually didn't find any provisional pods, so it kind of stopped there. As we can see here again, another node is coming up, and it's currently being bootstrapped and provisioned, and should get added to the cluster in a bit. So as you can see, the instance type is as requested, and it's going to 1C zone. So let's have a quick look. As we can see, the containers are already being created. And let's wait a couple more seconds. So we get the image downloaded. You would expect quicker response times from the cloud providers, but I'm sure it's going to be running soon. So yes, we have it running. So what we can do actually now is, like I mentioned before, it does attach a kind of a lifecycle hook sorry, a analyzer to the node lifecycle hook. So if we decide to say, okay, we're gonna terminate one of the nodes, let's pick this one, and say, okay, we're just gonna delete the node, right? We don't want this node, or you can imagine the TTL expired, so the node expired, it's just gonna go away. And what is going to happen here, you're going to see, as I said before, there is a termination controller, which is kicking in now because of the finalizer. It's been kind of triggered, and it cordoned the node. So the node has been cordoned, and the pods are currently being evicted from that node to the rest of the capacity. Because we provisioned enough capacity that can fit all the other nodes, so all the nodes can actually be scheduled. And if we check the pods again, obviously all the pods were successfully scheduled to the existing node. And we should actually end up with only one node kind of serving the whole capacity, which is what we expected. So you can see it's kind of nicely interacting with manual interactions as well. Okay, let's say let's quickly scale that down to 0 and see what happens now. So if we check the pods now, you're going to see all the pods are being terminated at this point. And as soon as all the pods are terminated, if we look at the controller, it has detected the underutilized node, or better say the node was empty. And it added a TTL to that specific node saying the node is empty, let's mark it with a TTL. And if there is no workloads going to be scheduled in the next 30 seconds, it's gonna start terminating the node. Obviously, it's gonna first cordon it as usual and then delete the node. And this actually deletes the node, not just from the cluster, but also in underlying cloud provider as well. Okay, what else can we do here? So let's say we don't want to use the x64 architecture, and we want to use the ARM64. So what we're going to do, I'm just going to quickly patch the deployment. So I'm going to change or add the node selector to our deployment, saying that our pods need to be provisioned on ARM64. Let's scale that up now to 1 first. So what we're going to notice here is the allocator controller initially kicked in, found there is a pod that needs to be provisioned. Obviously, it wasn't scheduled, and it immediately started provisioning a new node. And based on the original constraints, it only picked from the ARM nodes that we specified in the provisioner, and we only kind of limited to 4 of those. And based on the requirements, it picked the smaller one that can actually fit everything in. And as you can see here, it's already being provisioned. And like I said before, in around a minute or so, the node should be up, added to the cluster, and ready to take on the workloads that are currently being waited to be scheduled. So I'm just quickly going to see. Yeah, it's still pending. If we switch back to our nodes, so about a couple of seconds more, and the node should be up. Here we go. It's using the Graviton instances, and it's being provisioned to EU West 1A. And if we have a look at our pods, as you can see, the container is already being created. So the pod was obviously scheduled, and it should enter the running state immediately. So just before we wrap it up, what I want to show you is as well how quickly it reacts to changes. So let's say we want to scale up to 100 instances, right? Which might seem a bit absurd, but if we check, you can see we have all those kind of pods in a pending state. And Carpenter is initially kicking in, finding the resources we need to kind of satisfy that, and immediately start kind of initializing the bootstrapping of the nodes, and kind of bounding the pods to nodes already. So as you can see, it immediately added additional ARM nodes, which are going to be provisioned, and the pods are going to be, as soon as that provision, the pods are going to be assigned and kind of run on those nodes. So I think I'm kind of running out of time slowly, but I'm just going to wait a couple of seconds just to kind of show you that we are running the capacity we kind of requested. It's limited to the AZ that we wanted to. It's using the largest capacity available from the list. and we should be getting our workloads kind of scheduled immediately after the nodes are available. So as you can see, the containers are already being created. Cool. All right, that concludes the demo. I'm going to quickly switch back to my slides. There is one more left. So there is quite a really good roadmap available on the GitHub. So quickly, what the plan is, so for the rest of the year, so for Q4, the plan is to support all known use cases and rigorously kind of test for scale and performance. And there is some work left for the future as well. So as I said, they want to improve the heuristics, and there is the fragmentation that's still missing. And there needs to be a better kind of AMI support, because currently they're only supporting BottleRocket or the Linux 2 AMIs from Amazon. So for my talk, what I really want to kind of summarize on is capacity planning is really hard. It's not easy. And what we get by using a solution such as Carpenter is it eliminates the node group kind of requirement, kind of breaks the typical kind of constraints there. It directly kind of requests for the capacity, which gives us the flexibility and also the efficiency. It lowers the complexity of configuration. It's portable by design and quite performant as well. So going back to the quote, it definitely seems like water-like scaling. So trying to reduce and avoid friction with, working closely alongside with existing kind of concepts like Kube Scheduler and efficiently responding to dynamic requests from the environment. I'm going to share the slides afterwards, so I'm going to leave you some further reading, and please do keep in touch. And I'm happy to answer any of the questions that might come across. Back to you, Adrian.
Oh, thank you very much, Marko. I think that was excellent. There's a lot of in-depth knowledge there. And yeah, I think it's one thing that trips up a lot of people. They don't realize how hard scaling is. We do have a question from Tim Bannister, who asks, can I use Carpenter to skew (bin pack) my workload onto the most cost-effective set of nodes? What other components would I need to make that work?
So yes, they would automatically try to pick the most cost-effective instance types that you're limited to. So you can already achieve that. But like I mentioned before, unfortunately, the fragmentation is not implemented yet. So you would end up with the initial kind of resources that would be provisioned, and it wouldn't be kind of optimized for the workloads. But if the nodes get emptied, that would definitely get kind of shut down, and it already works like that. Okay, excellent.
I do have another question. So are you a big Bruce Lee fan then?
Not a really big fan of it, but I do like the philosophy behind it. So yes, that's why I actually picked the quote. So yeah, I think it really kind of nicely kind of goes along with the zeitgeist of this project. So yeah. Okay. How about you? Are you a fan of him?
I do I quite like Jackie Chan as well. Some of those movies are fantastic.
Cool. Yeah, absolutely.
I appreciate the philosophy as well. Okay, I'm going to hand back to Danny now, because I believe we have another message to read out.
Yes, one more message for Control Plane, who's the final sponsor for the event. So Control Plane are a London-based cloud-native technology company, and they help to keep people safe online. They work with cloud providers, banks, insurance companies, and governments to secure the building blocks of the internet with consulting, training, and products related to cloud-native development, security, and operations. They're trusted by Google Cloud, the UK Home Office, JPMC, among many others. Their clients are world-leading organizations. So thank you very much to Control Plane for sponsoring Kubernetes Community Days UK 2021. And with that, I would like to hand back to Paula for the final conclusion slides.